In this CircuitPython tutorial, I'm going to build a battery-powered Bluetooth BLE remote control to operate a BLE peripheral that hosts a solenoid and a light detector. This will be a fast-paced video, but a full write-up will be available online, which will be linked in the video description. This tutorial covers BLE two-way client-server communication between two nRF52840 Feather boards. A Feather will control a solenoid using a logic-level MOSFET. A spectrally selective light detector will be implemented using a low-cost LED. The Adafruit debouncer library will be used to debalance a push-button input switch, and smooth NeoPixel animation will be performed using the fancy LED library. Here's the surveillance camera server that's located in a locked closet. Currently, the only way to turn it on is by pressing this power button on the front of the case. My goal is to build a BLE peripheral that can attach to the front panel so I can turn it on remotely from outside the closet. I also want the peripheral to wirelessly report whether the server is on or off. There are several ways to determine if a device is powered on, such as a non-contact current sensor or measuring voltage on the PCB, but I think the least expensive and the least likely to avoid the warranty will be to detect if the blue light on the push button is illuminated. An LDR, or light detecting resistor, also called a photoresistor, would work. They're often used in circuits that detect if it's day or night. However, their sensitivity varies with the light wavelength, and there are other lights in the closet that could interfere. I tested an Adafruit RGB color sensor, and it was able to distinguish the blue LED on the front of the case, and it is easy to implement in CircuitPython. However, there's a simpler and cheaper solution. LEDs, or light-emitting diodes, are great for emitting light, but they can also be used for detecting light. Many electronic devices can be reversed. For example, a motor can be powered by electricity, or it can generate electricity. A speaker can also be used as a microphone, and an LED will generate current when exposed to light. Additionally, LEDs are spectrally selective. In other words, they can detect specific colors of light. Generally speaking, LEDs are most sensitive to the light that is lower than the dominant wavelength they emit. Therefore, a yellow or red LED may yield the best results for detecting a green LED. Likewise, an aqua or green LED could be used to detect blue light. My testing found that a sensing LED with a wavelength 50 nanometers greater than the emitting LED worked best. If you don't know the wavelength of the emitting LED and you don't have an expensive spectrometer, it can easily be found using a diffraction grating, such as this slide, which costs under $1. Place a ruler directly in front of the LED to measure. Then position the slide at a known distance of at least 5 feet from the LED. Longer distances tend to get better results. Looking through the slide, you'll see that some of the light gets diffracted. The ruler in front of the LED can be used to measure the distance from the light source to its nearest neighbor, either left or right. In this case, the value is 5.875 inches. The wavelength represented by lambda is equal to this formula, where d is the distance between slits in the diffraction grating, y is the distance between the LED and its nearest neighbor, and L is the distance from the slide to the LED. My diffraction grating slide has a value of d equal to 4,850 nanometers. If you don't know this value, it can be determined by solving for d with an LED of known wavelength. The distance to the nearest neighbor y is 5.875 inches, and the distance from the slide is 60 inches. The units cancel out, so it doesn't matter if you prefer metric. Plugging in the numbers gives a wavelength of 472 nanometers for the blue LED on the surveillance server power button. Therefore, an LED 50 nanometers higher, or around 522 nanometers, should work well as a detector. I'll use a Broadcom high-intensity green LED with a wavelength of 525 nanometers. It has a narrow 15-degree viewing angle and a water-clear lens, both of which should improve the sensitivity. Wiring the LED to the nRF52840 Feather is very straightforward. The LED will generate a voltage when it detects light. Therefore, the LED anode is connected to A0, which is one of the 6 analog-to-digital pins on the Feather that can read voltages and convert them to a 16-bit value. Next, the Feather's ground is connected to a ground rail on the breadboard. The LED cathode is also connected to the ground. As is, this circuit would be very noisy and unreliable. Therefore, a filter is added comprised of an 82 nanofarad ceramic capacitor across the anode and ground, and a very weak 15 million ohm pull-down resistor also between the anode and ground. That's all it takes for the detector circuit. The Feather should now be able to read a voltage change on A0 when a bright blue light hits the attached green LED. A mini 5-volt push-pull solenoid will be used to press the button on the front of the surveillance server. The solenoid is an electromagnet. The metal rod in the center, also known as an armature, will be drawn into the solenoid when power is applied to the coil. When power is cut, the spring will return the armature to its starting position. The solenoid draws 1.1 amps, which is much more than the GPIO pins on the Feather can source or sink. Therefore, a logic-level N-channel MOSFET will be used to drive the solenoid. The MOSFET can act like a switch. When enough voltage is applied to the gate pin, it allows current to flow between the drain and the source pins. An IRLB8721 is selected because its gate can be driven at logic level voltages, such as the 3.3 volt GPIO pins of the nRF52840 feather. The solenoid and the MOSFET are easy to wire up. The 5 volt USB line on the feather is connected to a 5 volt rail on the breadboard. One lead from the solenoid is also connected to the 5 volt rail. The other solenoid lead is connected to the MOSFET drain pin. The MOSFET source pin is connected to ground. Now when enough voltage is applied to the gate, it'll complete the circuit and the solenoid will activate. The MOSFET gate will be controlled by GPIO 13 on the feather. An optional 10K ohm resistor pulls the gate to ground. This mitigates coupling capacitance and ensures the solenoid will not activate if the gate is allowed to float. Finally, a 1N4004 snubber diode is placed as close as possible to the solenoid leads with the cathode on the positive side. The diode protects the circuit. When power is cut to the solenoid, the electromagnetic field collapses and can generate a substantial flyback voltage, which could damage the MOSFET or other components. The snubber diode dissipates this current. Eagle was used to convert the breadboard to a PCB board design, with female headers to accommodate the feather, and two 2-pin JST connectors for the LED and the solenoid. I etched the board myself using a laser printer and muriatic acid. However, there are many online services that can prototype a PCB for a very reasonable fee. You could also use a perf board. SketchUp was used to design a bracket to hold the PCB to the front of the surveillance server. There's a slot to secure the solenoid over the push button. On the side is a through hole for the LED light detector. The bracket will slide over the front of the server. Threaded rods will mount through the holes on the side and secure it to another bracket in the back. I 3D printed the brackets. I used black PLA filament to match the server color. Here's the mini 5V push-pull solenoid. It fits snugly into the slot on the bracket, but just to make sure it doesn't wiggle loose, I also printed a small cover plate to secure it. The plate is secured with a screw that self-taps into the hole next to the solenoid. When activated, the solenoid will only travel a few millimeters, but it's enough to engage the server's power button. Here's the etched PCB with the components soldered on. It snaps into place on front of the bracket and is held down by clips on top and bottom. The male JST PH plug from the solenoid goes to the right connector. I soldered the green LED to red and black wires with another male JST plug. The 5mm LED snaps securely into the side hole in the bracket. It then plugs into the left connector, and there's a clip to manage the wires. I soldered male header pins to the Adafruit Feather nRF52840 Express. It plugs into the matching female headers on the PCB. M5 x 250mm fully threaded stainless steel rods will secure the brackets. I'll slide the rods with nuts on one side through the back bracket. Next, the front bracket is slid onto the other side. 2 additional nuts will retain it and allow for adjustments to fit the server case. The assembly slides over the server and the nuts are tightened to hold it in place. The design affords easy adjustments to ensure the solenoid and LED are correctly positioned over the illuminated power button. Okay, the peripheral hardware is ready to go. Now let's write the CircuitPython software to control the solenoid and monitor the LED via Bluetooth. I'll write the software on a Raspberry Pi connected to the Feather using a USB cable. Before coding, a few libraries will be required. I've already downloaded the latest CircuitPython bundle to the Raspberry Pi's download folder. The first prerequisite is Adafruit Bluefruit Connect, which provides several helpful protocols for BLE communication. In another window, the Feather's lib folder is opened. Now just drag and drop to copy the library to the Feather. The Adafruit BLE library is also required. However, the BLE scanning and client features are currently being alpha tested and are not included in the bundle. In the future, they'll probably be added, but for now they need to be downloaded separately by going to the Adafruit CircuitPython BLE GitHub repo. Click Releases. The required version was just released 5 days ago. Expand the Assets section. Then click to download the 5X alpha. Once the download completes, return to the Downloads folder and extract the zipped BLE library. Navigate into the lib folder and then to the Adafruit BLE folder. Confirm that the required scanner and UART client libraries are present. Go back up one level and copy the Adafruit BLE folder to the Feather. Now we can start coding. Close all the open windows and open the Mu editor. Several imports are necessary. UART server is imported from Adafruit BLE. Packet is imported from Bluefruit Connect, in addition to button packet and color packet. From board, the pin references for A0 and D13 are imported. From analog I/O, import analog in, which will be used to read the analog to digital port. From digital I/O, import digital in/out and direction, which will be used to control the GPIO port. From time, import sleep. A variable called LED is set to analog input 0, which is connected to the LED. A variable called Solenoid is set to GPIO pin D13, which is connected to the MOSFET controlling the solenoid. Direction is set to output. A high level of 3.3 volts in the GPIO pin will activate the solenoid. A low level of 0 volts will deactivate it. Value is set to false, which equals 0 volts, so the initial state of the solenoid will be deactivated. A BLE UART server is instantiated. The main loop is an infinite while. Advertising is started on the UART server. Another while loop pauses the program until a BLE client connects. Another loop will run as long as the client stays connected. The in-waiting property checks if any client data is present in the UART buffer. If so, the data is cast to a packet variable. Is instance is used to determine if the received packet is a button packet. If so, and button number is 1, and it's pressed, then the solenoid is turned on for a second and then turned off. Next, a variable called LED intensity reads the LED voltage, which is converted to a 16-bit integer between 0 and 65,535. A Boolean variable called LED on is set to true if the intensity is greater than 1000. Otherwise, it's false. I tested the LED voltage on A0 while it was exposed to blue light. The 16-bit reading was around 10,500. This equates to 528.7 millivolts. Without any light, the reading on the analog input dropped to 0. The ADC will pick up some noise, but with the filter, the readings never exceeded 100, which is around 5 millivolts. I set the threshold at 1000, which is 50 millivolts. Therefore, it's an order of magnitude greater than the noise, and still an order of magnitude less than the typical LED on voltage. This may seem conservative, but there could be temperature fluctuations, and the sensitivity of the LED as a light detector might degrade over time, especially since I'm using a gallium nitride LED. Gallium phosphide or gallium arsenide might be more stable. Again, we only care about the LED's on-off state, so resolution is not too important. We're not trying to measure luminosity. Our color packet is defined, red for off and green for on. The color is set by specifying values between 0 and 255 for red, green, and blue. If LED on is false or 0, then not LED on will be true or 1. Therefore, if LED on is false, the red component will be 255, and if LED on is true, the red component will be 0. The not is removed for the green value, so if LED on is true, green will be 255, otherwise green will be 0. The blue component will always be 0. UART server write transmits the color packet to the remote client. This lets the client remote control know the on-off state. It's good practice to wrap all BLE serial communication in try statements to catch errors. Finally, the loop sleeps for 200 milliseconds and repeats. I'll open the serial console and click Save. The program is called code.py, so it'll run automatically. Click Save, the program auto-reloads, and no errors. Next, let's build a remote control which will be used for the BLE client. The client will just be another Adafruit Feather nRF52840 Express board. The board comes with a built-in NeoPixel and push-button switch, so no external components will be required. It also has a LiPo battery jack and charging circuit, so the remote control can be battery operated. Adafruit provides free modular case designs on Thingiverse to house the Feather boards. The STL files are easy to modify and 3D print. Here's the 3D printed parts. The new Feather board screws into the middle container. There's an opening for the micro USB port, which will be used to charge the battery. The bottom container holds the battery and an on-off switch. The default design had a mini slide switch, which I modified to a mini rocker because I prefer the more defined throw. There's a hole for the battery connector cable, which plugs into the JST jack on the board. When the switch is turned on, the battery will power the Feather. The two modular containers snap securely together. It is a tight fit. I drilled 2 holes in the case lid. I inserted a black nylon screw through one hole and secured it with a nylon standoff. It will actuate the built-in push-button switch on the Feather. The other hole will hold a segment of 2mm N-Glow fiber optic filament. This will act as a light tube for the built-in NeoPixel on the Feather. The lid snaps into place and the filament should be directly over the NeoPixel and the nylon screw over the push button. When I flip the rocker switch, the filament illuminates brightly. When I press the nylon screw, I can hear and feel the switch below engaging. Okay, the remote control hardware is complete. I just need to write the Bluetooth client software for it. Back on the Pi, I replaced the server Feather with the blank client Feather. The empty lib folder requires several libraries. From the CircuitPython bundle lib folder, Adafruit Bluefruit Connect is selected. Also Adafruit Fancy LED for creating smooth LED animations. Adafruit Debouncer facilitates polling and debouncing switches. The NeoPixel library is required to control the Feather's built-in NeoPixel LED. Drag and drop the 4 libraries to the Feather's lib folder. Next, navigate to the pre-release Adafruit BLE library and copy it to the Feather. Afterwards, close the windows and open Mu. In the previous BLE server code, UART server was imported. Since the remote is the client, UART client is imported. Scanner is imported. This allows the client to find the server. Packet, button packet, and color packet are imported. The NeoPixel library is imported. The board definitions are imported for the built-in NeoPixel and user switch. The switch to bouncer is imported. Generally speaking, when a mechanical switch is pressed, it doesn't just change from open to closed. The metal contacts actually oscillate for a few milliseconds. This can trick a microcontroller into reading multiple presses. The debouncer suppresses these erroneous readings. Digital in-out, direction, and pull are needed to pull the user switch. Sleep is imported. And the Fancy LED library is imported as Fancy. A GPIO pin is defined and set to the built-in user switch. The direction is set to input because the switch state will be red. The built-in pull-up resistor is turned on, which prevents the switch from floating. The unpressed state will be high, and the pressed state will be low. A debouncer called switch is defined and passed the pin. A NeoPixel called pixels is defined and passed the definition for the built-in NeoPixel. One indicates that there's only one LED. Several colors are defined: aqua, green, orange, red, and blue. 2 gradients are defined. Off will fade from red to orange, on will fade from green to aqua. The default palette is defined using the Fancy expand gradient method. It's past the off gradient. 30 indicates the total shades of color. Gamma levels are defined for red, green, and blue. Color index will track the current palette color. Fade direction will track fading, 1 for up and -1 for down. For example, red to orange versus orange to red. Target stores the Bluetooth server address. Each BLE device is unique. There are several ways to find your address. Nordic makes a free app called nRF Connect. It has a scanner function that will enumerate all devices in range. The Feather should have a name that starts with CircuitPy. A button packet labeled 1 is defined, with press set to true. A BLE scanner is defined, and a UART client is defined. The main program loop is an infinite while. An empty list of UART addresses is defined. The NeoPixel LED is set to blue to indicate a disconnected state. The LED doesn't actually change color until the show method is called. Another while loop waits for the BLE device. UART client scan returns the addresses of all devices in range. The program loops through the returned addresses and searches for the previously defined target address. Once found, UART client connect is used to connect to the peripheral device. 5 is the timeout in seconds. Another while loop runs as long as the client stays connected to the server. Switch update polls the debouncer, then checks if the switch has entered a fail state, which indicates a new button press. If so, UART client write transmits the pressed button packet to the server. Next, in waiting checks the UART buffer for data received from the server, specifically for LED status color packets. Fancy CRGB pack is used to convert and compare the color packet to green. At this point, it'd be easy just to set the remote control's LED to green, but instead an animation will be initiated by expanding the on gradient, which will create a palette ranging from green to aqua. If the packet is not green, then the off gradient from red to orange is used. In addition to aesthetics, the fading LED also confirms the connected loop is functioning, which is helpful for debugging. Next, the current NeoPixel color is retrieved from the selected palette at the current index. Gamma adjust corrects the current RGB brightness to better match the response curve of the human eye. Pack converts the RGB value to a color integer. The NeoPixel is set to the current color, and then show updates the LED. If the color index reaches either end of the palette range, then fade direction is reversed by multiplying the direction by -1. The color index is incremented in the selected direction. Finally, the loop sleeps for 20 milliseconds and repeats. Open the serial console and click Save. Again, the program is called code.py, so it runs automatically. Click Save, program runs, and it doesn't look like there are any errors. It's a little hard to tell in the video, but the NeoPixel in the remote control is a solid blue, indicating the BLE client is not connected. I'll plug in the USB power cord to the peripheral board. The Feather lights up, and the BLE software should now be running and advertising, which should allow the remote to connect. The NeoPixel on the remote fades from red to orange, indicating the server is off. I'll press the button. The solenoid fires, engaging the power button for 1 second. The NeoPixel on the remote changes to the green aqua palette. The LED light detector successfully detected the blue power button light and updated the status on the remote control. I can still manually control the surveillance server by pressing in the armature. Holding it down for a few seconds initiates a shutdown. As soon as it powers down, the power button LED goes out and the remote control switches back to the red-orange palette. By the way, I'm testing the remote control next to the server for filming purposes, but I have tested the range outside the closet with the door closed, and it works great. I hope you found this video helpful. You can support this channel by leaving a like, sharing, and subscribing. Thanks for watching.